Hi guys, Dr. Tracy here to talk about sorting and searching. The topic for this week is sorting and searching, which are two very important parts of programming because when you have data, you need to be able to find what you have and how to get to it. And sometimes you would think that that's just an easy thing. I just go through each one till I find it. Well, actually, that's a very inefficient way to sort. If you can imagine, if I told you in a deck of cards, find the two of hearts. Well, brute force would say, I just go through every card and I look at it and see if it's the two of hearts. And when I get to the two of hearts, searching is complete. And sure, that works when you're looking through a deck of cards. 52 cards, you know what you're doing, and it's a quick process. But when you're dealing with thousands, tens of thousands of pieces of data, going through each one is not efficient, and it takes a lot of time. So instead, we develop other ways to be able to search, which involves first sorting and then cutting the searches in half, doing different methods of merge, sort, and so forth. Watch this video. I think this guy explains it pretty well, talking about how to sort things in order and to find the elements that you're looking for. We represent the speed of searching and sorting through something called Big O notation. And Big O notation, as listed here, plus an article, is what your discussion is this week. Big O notation measures the relative efficiency of a program by saying how long it takes to run it based on the number of variables that are used in the process itself. So in this topic, we are covering chapter 12. Let's move this over here so you can see this better. Okay, so chapter 12 is sorting and searching. And the main point of understanding sorting and searching is to create these algorithms and compare the algorithms based on the data that we're using to see which one is the best one for whatever we're doing. And depending on what you're doing, it may differ in performance. And so that's why we use Big O notation as a comparison. So let's talk about selection sort. Selection sort is the type of algorithm that will rearrange the elements into a certain type of a sequence. It starts with the smallest, and then it swaps the smallest with whatever element is first, and then it looks at the second and the remaining elements and keeps swapping in that selection sort. And this is an example of how that might look. So the computer, put things in order. It has to know how to do it. So let's say we have these elements 11, 9, 17, 5, 12. So it goes through and it says, is 11, or which one is the smallest? It's basically, you do some code. Figure out 5 is the smallest, so you swap 5 and 11. That's a selection sort. Now, of the remaining elements, which is the smallest? 9. 9 is in the right place, so we keep it there. Of the remaining elements, which is the smallest? 11. Switch 11 with 17. And of the remaining elements, which is the smallest? 12, so switch 12 and 17. That's how a selection sort would work. And here's the code that does basically that. It checks to compare each of the elements, finds the smallest element in the array, and switches it with the first position. And so you can take a look through that code to see how it is looping through each of those pieces. Oh my goodness, I just went way down. Hold on. Now, the thing about selection sort is it's a basic way to be able to sort data. But as you run programs, the more elements you have a runtime where Big O notation is going to be dependent on the number of data elements. So it becomes slow on large data sets because it has to go through, let's say we have 50 elements. It'll go through all 50 to find the smallest, then swap it for the first. Then it has to go through 49 to find the smallest and swap it for the first. Then it has to go through 48. So when you have 50 elements, it's going to have an exponentially large number of processes in order to make it work. So there are different ways of being able to create a sort. I'm going to move past this a little bit. The next one to talk about is the merge sort. So this analyzing performance stuff is about Big O notation and how we compare the performance. I'm going to let you read into that because that's part of your discussion this week. So in a selection sort, we are multiplying it exponentially. But another method of creating a sort is by, let me find the right. Another method of sorting data elements is using something called a merge sort. And in a merge sort, we kind of put it in half. And we just keep breaking it down to chunks in half until we get them in order on one or two, and then put them all back together. So the video that I linked on the page does a really good job of explaining a merge sort. But you see, it takes half the time. So if I take all those elements and divide them into two groups, if there's an odd number, they won't be even groups. But if it's an even number, they will be. So what you do is you take each of the elements, each of those groups, and divide them up into sequences, and then you can further divide it until you get down to whichever's the smallest. So instead of looking through all of them, I would now be able to take just the smaller groups and show what the minimum value of those are instead of looking at all 50. So two halves of arrays are then sorted instead of a whole array, and then they're merged back together in a recursive algorithm where you apply the merge sort to half the problem, you divide it again. And then you would apply the merge sort to half the problem and divide it again until you get down to just two cards or two elements, and you compare which one's the smaller or less. Now, once you do that, you put those back in the pile until you get a whole pile that's merged together in a merge sort. There is a merge function that's built into C++, but you should at least understand how it works. There's also a section that shows how to analyze a merge sort. In this section on searching, and that again is based on Big O notation. So in the section on searching, when you search for an element, if your data is not sorted, then finding an element will be harder. And really the only way to find an element is to go through each element until you find the one you're looking for. But if you have sorted elements, there are different algorithms that allow you to search. The basic search is a linear search, which is just start at the beginning and go through until you find it. That's called a linear search. It's also called a sequential search. And the code to do that just loops through for I equals 0, while I is less than size, I plus plus, meaning it goes through every element within a data set. Now that's also going to be slow because you'll assume that the speed of doing a linear search is going to be the average, which is the total number of elements divided by 2. So that is what the Big O notation is. But a binary search, if we knew these were already sorted, then we could use a binary search. And a binary search kind of breaks it in half, sort of like what the merge sort did. The binary search is going to say, let's put them in order and let's find the middle value. And is the middle value greater or less than the one we're looking for? And if it's greater than, we know that whatever we're looking for is within the first half, and we can eliminate the second half entirely. Okay, so that cuts it in half already. But then once we keep doing that and dividing the data elements in half and half and half and comparing greater or less than, we'll be able to find the element quickly while only going through one bit at a time. And so that's what a binary search example. You never visit all elements. And so when you create a binary search, you're always eliminating ones that it can't be. By doing that, you're taking these middle elements and you're making it smaller. So you're actually creating a Big O notation that's going to be based on a logarithmic number, which means it's much faster, but than a straight linear search, but because it's a smaller number. So if you have very few elements, if you only search a sequence once, you may as well do a regular linear search because you don't have to keep going back. But if you are going to make a number of searches in that sequence, then the binary search is going to be better. All right, well, that gives you an idea, and I think that you should definitely take a look at this video. The videos that I put in here are very helpful, especially this little British dude up here. Okay, I think he's pretty helpful. There's another couple ones about searching and sorting, and then also there's discussion on Big O notation. Hope you have a good week. Let me know if you need any help.